Matthew, we're just going, but at the slideshow is posted. You decide how you want to take notes. If you want to create a new notability document, take notes there. If you want to take it, there's a PDF of the slideshow in there that you can dump into notability and take notes on the slideshow. You can go paper and pencil, it's entirely up to you. Okay. Again, wrapping up in our last bit of review, we're going to talk about inverse functions and everybody's favorite, logarithms, right? Yay! The only thing that was loaded with sarcasm. Okay. Can you understand what it means to be one-to-one? What does it mean to be one-to-one? We'll jump the gun here and ask now while we're doing the objectives. What's it mean when a function is one-to-one?
Oh, one every output has one, or every input has one output.
Perfect. HLT? Horizontal line test. Inverse of a function. Graphing logarithmic functions. That's an L. So understanding Ln, natural logs. See, I put logs in the background of that picture. Very good. We're talking about logs in the back. And we're going to do some change of base. And we're going to do some inverse trig, one of my least favorites. But we got to do it at some point, so we'll go through it quick. If I go too fast, please slow me down, but I want to be sure to get this done, even though you've seen it before. As Brooke told us before, one-to-one, also known as injective. You're never going to be asked about that word ever again. It means for every x, there is exactly one and only one y. Okay. So a line would be one-to-one. A parabola is not, because for a certain y, there are two x's. All right, some notation. You know this already, but if I have a function f of x, its inverse is written as f to the negative 1 power of x. That is not to the negative 1 power. It's not a reciprocal. By the way, if I'm talking about the reciprocal of a function, I would write it this way. What am I doing? Let's try that again. That's a reciprocal. Okay. Reciprocal inverse. Don't confuse those. This is the big one that I hinted at earlier that we are now to it. The difficulty of finding a range of a function can be simplified by, remember, that simple number 2. The domain of a function is equal to the range of the inverse. The range of a function is equal to the domain of the inverse. So when we get those big scary equations and you're asked to find the range, finding an inverse is usually not a very difficult thing to do. If you can figure out what the inverse is and then find the domain, which you've all established being very adept at, then the range is done. Okay? So finding domain's easy, so we're just going to use domains and domains. The domain of the function or the domain of the inverse to get that domain and range. Does that make sense? Have you heard that before? Maybe? I think so. Okay. It's good enough for me. And then number 3, you know that the property of an inverse is that they undo each other. Right? Maybe give me an example of an inverse function. A function and its inverse. Something simple. Keep it simple, stupid.
Do you want actual numbers?
No. Just like give me a mathematical function and what's its inverse.
Okay, x squared.
Okay, and its inverse would be?
Would be y squared?
No. Let's back up. If you take the square function, what undoes a square function?
Square root. Well, if you take square root.
Square root, perfect. Those are inverse functions. Okay? If you take a square function, if you square something, you want to do it by taking the square root. Give me another one, Dimitri. Again, keep it simple.
Take the put it under the, I don't know, so when you, take the square root of it with the, like the board thing, you know, on the,
No.
just,
Square root,
yeah.
undo it with?
Uh,
So you took the inverse of her inverse. It's getting like some inception stuff going on here. Yes. Any others? What's the inverse of addition? Inverse of multiplication? Division. Okay, that kind of stuff. Okay? It simply undoes it. From a mathematical standpoint, the bottom line of that slide, you can check to see if two functions are inverses by building a composite function. Take one function, put it into the other. If you end up with x, you're good to go. And you have to do it both ways. So Maeve told us that a square function and a square root function are reciprocals of each other. So that means if I build a composite function, I'm going to take the square root function and put in x squared. What's that equal to? X. Good. Check. But you got to do the other one. Take the square root function and put it into the squared function. X. Check. We're good to go. Okay? It would be nice if they were that easy. They won't be, but that's okay. HLT. So now I'm going to be careful with the semantics and the language that I use. HLT, horizontal line test, checks to see if a function has an inverse. Sorry, I said that wrong. If a function's inverse is a function. I said it wrong the first time. Okay, so that seems like I said the same thing. All functions have inverses. The question is that inverse a function? And that's what HLT checks. And I don't know if you've used that language before in mathematics, because it's really easy to say, well, yeah, HLT just tests whether or not a function has an inverse. Again, all functions have inverses. What we care about is, does that inverse stay a function? Okay. So, for instance, the x squared graph. If you go to a parabola, is the inverse of a parabola a function? The answer is no. Okay, and we'll talk about from a graphical standpoint why that doesn't work. And that's why when we graph the square root function, you just get the one curve and not the whole sideways parabola. Okay, so how to do that? And you've done this before. Interchange x and y in the functions, solve for y. That thing that you get at the end is the inverse. Please tell me you've done this, yes? Good, excellent. That's why I'm going through it quickly. And again, the two tips that'll help: the domain of the function is the inverse, is the range of the inverse, and the range of the function is the domain of the inverse. Okay, let's try one. There's a function. Please find its inverse.
Oh, now I'm so cold.
Oh, good. It's very courteous of you to ask. It's easier than putting the plastic back. Yeah.
I realized that I'm literally.
You start to land slow. While you're working, I'm going to ask a question. Last year, did you talk about what graphs of inverses look like? A little bit. Okay, we're going to spend a little bit more time on it because it's really important in this class. Are we all good? Sure. Posey, you want to help me out?
Yeah,
Okay.
I switched it, so I had under the square root of 2y minus 3 is equal to x.
That's a good start so far.
Then I squared both sides. I got 2y minus 3 is equal to x squared. Then I added 3 to the other side. I divided by 2.
Hey, let's give it up for Posey. That is the inverse function. If you want to get fancies in your pantsies, then actually, yeah, we're going to use the notation there and say that that is f inverse of x. Excellent. Now, if I didn't believe Posey, I could take that and plug it in there. Sorry, wrong place. Plug it in there and make sure that my answer ends up as X, and then do the reverse. But we're going to trust the system, switch the X's and the Y's, solve for Y, you're good to go. Questions? Excellent. Let's talk about pictures. There we go. The thing to remember most about inverses for our purpose is that a function and its inverse are reflections of each other over the line y equals x. Okay, that was a big mouthful. You see the line y equals x, it's at 45-degree angle, the dashed line. If you take a function and graph its inverse, they are reflections of each other over that line. Okay. And that's something I'm going to tell you now in week 2. We're going to use it again in month 2, and you're going to forget about it, but we'll get there eventually. The inverse and its functions are reflections of each other. Which, if we go back to the previous conversation, if we start with a parabola, the standard x squared parabola, and we graph its reflection over the line y equals x, we get something that looks like that. Those are reflections, and you'll notice that the blue all of a sudden isn't a function anymore. It does not pass the horizontal line test. Why doesn't it pass the horizontal line test? Because if I go back to the original function, I can draw a horizontal line through just about anywhere and have it hit in 2 points. Okay. Theoretically, that's review, yes. But you told me you may not have done a lot with the graphing stuff, right? Okay. So most of the time when we talk about this function thing, we're going to get rid of that bottom guy and just stay with the one curvy thing so it stays as a function. Okay, so it's the difference between having x equals y squared. I think I talked about this, right? The difference between x equals y squared and y equals the square root of x. Does that sound familiar?
Yeah.
Okay. The top part is the square root of x. The whole thing is x equals y squared. Okay. The other thing is, which is in the way, a little bit of, maybe you talked about this in geometry, but if you take a point on a graph and you reflect it over the line y equals x, the coordinates change. Okay, so if this point is 0, -1, when I reflect it over the line y equals x, it becomes -1, 0. So the coordinates change places. We'll also use that later. This point right here is 1, 1. You get it, okay? A blue rectangle. We got some calculus speak going on there. A function can only have an inverse that's a function if it's 1-to-1. And then f is strictly monotonic on its entire domain. Then it is 1-to-1 and therefore has an inverse function. What does strictly monotonic mean? You have no idea, do you? Maybe you do. Let me guess, it's in the slideshow. Did I include it at the bottom, Daniel? Are you just going to read to me? Oh, I didn't. All right, good. What is it? Daniel?
I thought that if the equation has f in it, it must have a inverse function.
Yeah, but what does monotonic mean? Liam?
Isn't it the same thing as 1-to-1? I mean, if it only has... Okay.
No, it's a good guess, though. Always increasing, always decreasing.
That makes sense.
Okay? And we talk about increasing and decreasing. So, for instance, a parabola is not strictly monotonic. It goes down, and then it goes up. However, the square root function is strictly monotonic because it's always getting bigger. Exponential graphs are strictly monotonic. Lines are strictly monotonic. Assuming it's not horizontal or vertical. Another fancy smancy terminology thing you might forget about, but we will try to use that. Use the verbose language as we Horizontal line test we talked about already, we know that, beat a dead horse here, yeah, great, okay, logs. I don't know if you knew this, but the log function is the inverse of the exponential function. So we talked about exponential functions, the spread of disease, the zombie invasion. Okay. Times 2, times 2, times 2, times 2, times 2, over and over again. The blue is an exponential function. Strictly monotonic because it's always increasing. If you reflect that puppy over the line y equals x, you get the green line, and that green line is what becomes a log function. This one happens to be log base b, it could be just about anything. And I'm sure you did logs last year, so we're going to go through it quickly. That is log notation, that happens to be log base 5. What if there's no number where the 5 is? It's assumed to be 10. And what does that number become in order to get a natural log? E, our friend E from the other day. What is E again?
45, 80, 45.
Some people just remember little tidbits about the $20 bill and they just shout it out. 2.718281828 459045. Okay, good. You'll recall, with all the fun that you did last year with logs, if you take the log of a product, it is the sum of the logs. If you take the log of a quotient, it's the difference of the logs. Okay? And then last but not least is change of base form. Especially when we get to stuff with calculators. Your calculator will only do log base 10 or log base E, also known as the natural log. So if I give you a problem involving log base 7, for instance, you're going to have to convert to one of those bases. Normally, we're going to use natural log for no particular reason, just that it's more common than log base 10. So for instance, if I wanted to know what is, if I want to know what log base 7 of 12 is, using my calculator, I would write that as the natural log of 12 over the natural log of 7. And you can make that base whatever you want. Okay, I could actually write it as log base 2 of 12 over log base 2 of 7. But of course, you're all smart enough to know that that's a complete waste of time because I can't figure that out because my calculator won't do log base 2 without a lot of work. Okay, and that's why I stay with the natural log. How we doing so far? Good. Okay. Get it? Anybody? Kush, a little help, please? Could you explain that, please, to people that don't know? I went old school and found a picture. It's not mine. It's a Clash of Clans base. Get it? We're doing a change of base. It's a base, Clash of Clans. Kids, it doesn't get much better than this. So just revel in this. I don't think we need to do this because I just did, and I'm assuming that you can all type natural log of 5 divided by natural log of 8 in your calculator. Is that a safe assumption? Good. I pretty much answered my example on the previous slide because I got a little hyper. It happens sometimes. I'm excited about math. Inverse trig. Well, this isn't fun. Oh. Okay, so let me summarize this chart very easily. When you do the inverse of a trig function, you've done this a ton of times. When you do the inverse of a trig function, the trig answer gets restricted to certain quadrants. Okay? The quadrant restrictions are over on the right. Notice, you always get an answer in quadrant 1. That makes us happy. Number 2, you never get an answer in quadrant 3, as verboten. So therefore, the other quadrant comes from the negative sign of the function. Does that make sense? No. Okay, so if I'm doing an inverse sine relate to y or x? It relates to y. So if I already have a positive y in quadrant 1, where is y negative? Quadrants 3 and 4, but no quadrant 3. That's verboten. So therefore we go to quadrant 4. Okay? So this is the difference between memorizing and understanding. I've given you a way to figure out what other quadrants you're looking for. If that makes sense to you, great, but I'm not stupid. Some of you are just going to go home and try to memorize that. That's okay. Whatever works for you. Cosine relates to x. Where is x negative? Quadrants 2 and 3. No 3. We're in 2. Okay. Tangent, cotangent, a little weird because you could go in either one, but they're right there. Okay. So, what's the what's the arc cosine? Please tell me you did both, right? You know arc cosine and you know cosine to the -1 notation? Have you ever seen arc before? Okay. It's okay if you haven't, I'll just explain. Arc and these are the same thing then. Arc and this are the same thing. Just a different way of writing inverse. Normally, if we were finding the cosine of let's say cosine of pi over 4, I'm asking you, I have this location on the unit circle of pi over 4, what's the value? The inverse goes backwards. Here's the value, where is that located? What's the answer? This is awkward.
What?
Does everybody get it? The question is, what's the answer?
So, it's cosine. I thought it was theta. I was like, what? Okay. That. Yeah.
But we just go with pi over 2. Unit circle stuff. I don't want to beat a dead horse. I'm going to skip it because I want to get to this one, which is more exciting. How would you solve that? 0.3 is not a value on the unit circle.
Type into a calculator.
What's that?
I said type into a calculator.
100%. Type it into a calculator, get 0.305. The following phrase you will hear me say at least 1,000 times before May. In calculus, everything gets rounded to 3 decimal places. You have to be accurate to 3 decimal places. You ain't gonna like that. So if you tell them the answer is 0.304, that's pretty darn close, you ain't getting it right. So be careful. That's gonna take some practice. Ooh. Combining functions with inverse functions. If I take the arcsine of the sine of an arcsine, what are they going to do to each other? Cancel. Easy peasy, yes? Squaring a square root cancels. Yeah, it's not going to be that easy. What about that guy?
It makes sense.
Why is that different? The reason that's different is because where is negative pi over 4? What quadrant? 4. Cosine doesn't play with quadrant 4. So what do? No, you gotta grind it out. Where's the cosine? What's the value of the cosine of negative pi over 4? And then take the inverse cosine of it.
Oh, right. Yeah.
Okay. That's all. When in doubt, do the math. Don't assume that a function and the inverse are going to cancel each other. Okay, because you might not be in an acceptable quadrant. I think this is my last example. What happens when it's not a pretty number that's on the unit circle? We go back to the old trig, triangle, guide thing, stuff thing there. Yeah. That wasn't even English. I know that there's some angle that I'm calling theta. It's a little hard to see in the picture. And if I take the cotangent of that angle theta, I get, as Grandpa Selmer would say, 2 turds. And I also know that cotangent is adjacent over opposite. So I set up my triangle. How do I find the hypotenuse? Heck yeah, you do. Pythagorean theorem, 2 squared plus 3 squared equals hypotenuse squared. That's the square root of 13. Now I got my triangle and I can do whatever function I want. I can do all 6 of them. I'm feeling saucy. I chose cosecant just for giggles. Okay. You could have also, well, never mind, I'm not going to, that'll just complicate things. We'll leave it at that. If it's not on the unit circle, draw a triangle, do some geometry, do some Pythagorean theorem. Be careful when you're doing Pythagorean theorem. If you're not solving for the hypotenuse, one of the questions you might want to ask yourself is self. Should that answer be positive or negative? Because remember, when you take the square root, in this situation, it could be positive or negative depending on what quadrant you're in. This one easy peasy because the hypotenuse is always positive because that hypotenuse represents the radius of the unit circle or the circle on the graph. Okay? More. We did this already. Okay, now just throw in a variable. Great, Pythagorean theorem. Okay, excellent. Find that. Yeah, yeah. Okay, there we go. Get it? What are those? What are they? What kind of logs? No.
Natural log.
They're natural logs. Again, this is as good as it gets, kids. Okay. Oh! Look at how perfect that was! Just, I could have talked longer. I should have turned around. Now you go away. There we go. Okay, so usually on quiz day, you'll come in and find the desks lined up in rows. However, it's really hot today, and Everett and I were too lazy to move the desks. So we're going to do the old set up your little fort thing. So I'm going to ask Brooke to move away from the end because it's too easy for Lauren to cheat off of you. And then I'll pass out dividers. A lot of what we're doing here is the honor system. So let's not play games with the old, oh, I have to stretch my back. Okay, just work on your paper. It's okay. No, Brooke, put that desk back. Come sit over here.
Oh.
That'll be a lot easier.
Is that first quiz? I want to do it like a partner.
The good thing is you won't. What's the matter?
I do like a partner quiz to celebrate, our first quiz on
You can do this as a partner quiz.
Wait,
It's fine. Yeah, just give a 0. Correct. It's called cheating.
We're really good. Jokes don't stop.
This quiz happens to be non-calculator. So the only thing you need sitting in front of you right now is a writing utensil. Matthew, I'm going to make you take this because it'll be fun. I won't count it for a grade though. I just want to see what you can do. Okay? You all right? You look like you're going to throw up. You okay with that? You're good? Okay.
Where'd my name tag go? I don't know. Where did your name tag go?
Anymore, it's just like board.
No, your name was.
Yeah, it's literally board.
I got it. Does it matter? Okay. 1. That's 47 plus.
Just a blank page that says what? It's just a blank piece of paper that says why is there something instead of we spent less than 90 minutes.
Yeah, these ones are like really
You're gonna put like the X-ray nods in this.
Here, go ahead. Better over here.
Go ahead.
You guys get to for the next sleep. That's not
Okay, so again, You only have a pencil, you don't need, this is not a calculator quiz, make sure you put your name on it. If you have any questions whatsoever, come up and ask. The worst I can tell you is, sorry, you're out of luck. When you're done, bring it up to me, and then, like I said, you've got day 4 to work on, and or cleaning up day 3. Also, before you leave today, make sure you've already submitted days 1 and 2, because those are due today. Are you with us? No? Yeah. Sorry.